Hello there, and welcome to Sleepy Answers. Tonight, we're drifting into one of the most mysterious, beautiful, and genuinely mind-bending concepts that human beings have ever encountered. We're exploring infinity, not just as an abstract idea, but as something that sits at the very edge of what our minds can comprehend, pushing against the boundaries of logic, mathematics, reality itself. If you find these quiet journeys into the unknown meaningful, I'd love it if you'd consider liking this video or subscribing to the channel. It helps others discover these thoughtful explorations, one curious mind at a time. But for now, all you need to do is settle in. Let your thoughts drift. Allow yourself to wonder. Let's begin. Infinity is not a number. It's not a place. It's not even really a thing you can point to and say, there it is. And yet, infinity surrounds us. It hides in the space between numbers, in the endless march of time, in the question of whether the universe has an edge or simply goes on forever. Infinity is the concept that breaks mathematics, that challenges physics, that has caused philosophers to argue for thousands of years. It's the idea that has driven some of the greatest minds in history to the edge of madness, while simultaneously opening doors to entire new worlds of understanding. When you truly contemplate infinity, when you let your mind try to grasp what it means for something to have no end, no boundary, no limit whatsoever, something strange happens. Your thoughts begin to circle. They reach out, trying to find the edge, and there is none. They try to count to the end, and there is no end. The very act of thinking about infinity reveals how beautifully limited our minds are, and yet how remarkable it is that we can conceive of something so utterly beyond ourselves. Tonight, we're going to explore infinity from every angle we can manage. We'll travel back to ancient Greece, where philosophers first wrestled with paradoxes that still puzzle us today. We'll meet Georg Cantor, the mathematician who proved that some infinities are larger than others, a discovery so shocking that it was rejected by many of his peers and may have contributed to his mental breakdown. We'll check into Hilbert's Hotel, a thought experiment where a fully booked hotel with infinite rooms can always accommodate more guests, revealing the strange logic of the infinite. We'll peer into black holes where infinity seems to tear apart the fabric of space and time itself. And we'll ask the biggest question of all. Does infinity actually exist anywhere in reality? Or is it purely a creation of the human mind, a beautiful abstraction that helps us think about the universe but has no physical counterpart? So let your mind relax. Don't try to hold on to everything. Let the ideas wash over you like waves. Some will make sense. Some will feel impossible. And that's exactly how infinity should feel. The ancient struggle with infinity. Long before anyone attempted to write equations about infinity, long before mathematicians developed formal theories or physicists proposed infinite universes, human beings stared at the night sky and wondered, does it end? Ancient peoples looked up at the scattered points of light and confronted a question that was both simple and utterly profound. If you traveled far enough in any direction, would you eventually hit a wall, an edge, a boundary beyond which nothing existed? Or would you simply keep going forever, through endless space, never reaching any kind of conclusion? This question wasn't abstract. It was visceral. It touched something deep in the human psyche, this tension between our need for boundaries and our inability to imagine an absolute limit. The ancient Greeks were perhaps the first culture to really wrestle with infinity as a logical problem rather than just a poetic mystery. They had a word for it, apeiron, which meant unbounded or limitless. But they were deeply suspicious of it. The Greek mind loved order, proportion, harmony. The infinite was none of these things. It was wild, chaotic, fundamentally incomprehensible. It represented everything that couldn't be measured, couldn't be understood, couldn't be brought under the control of human reason. And so most Greek philosophers tried to avoid it, to argue it away, to prove that infinity wasn't really a feature of the world but rather a conceptual mistake. Aristotle, one of the most influential philosophers in human history, developed what became the standard view for more than 2,000 years. He distinguished between what he called potential infinity and actual infinity. Potential infinity was acceptable, even useful. It was the idea that you could always keep going, always add one more, always divide something smaller. If you're counting numbers, you can always count one higher. If you're dividing a line segment, you can always cut it in half again. This process never ends, but it never reaches infinity either. It's always finite at any given moment, just with the potential to continue indefinitely. This felt safe to Aristotle. It kept infinity at arm's length, as a process rather than a completed thing. But actual infinity was different, and it was dangerous. Actual infinity would mean a completed infinite collection, an infinite number of things all existing at once, an endless distance that somehow exists in its entirety. Aristotle rejected this completely. He argued that actual infinity was logically impossible, a contradiction in terms. How could something have no end and yet exist as a complete whole? The very idea seemed to violate basic logic. And, for the most part, Western thought followed Aristotle's lead. Actual infinity was dismissed as a philosophical error, something that might seem possible in abstract thought, but couldn't exist in reality and shouldn't be taken seriously in mathematics or science. Yet one Greek thinker demonstrated just how troubling infinity could be, even if you tried to avoid it. Zeno of Elea, a philosopher who lived in the 5th century before the Common Era, constructed a series of paradoxes that used the concept of infinite divisibility to create logical puzzles that seemed impossible to solve. These paradoxes have haunted philosophy and mathematics ever since, because even though we think we've resolved them, they still feel profoundly strange when you really contemplate them. The most famous is the paradox of Achilles and the tortoise. Imagine that Achilles, the swift-footed hero, decides to race a tortoise. Being a fair sportsman, he gives the tortoise a head start. Now, Zeno argues, Achilles can never overtake the tortoise. Why? Because first Achilles must run to where the tortoise started. But in the time it takes him to do that, the tortoise has moved forward a little bit. Now Achilles must run to that new position. But again, while he's doing so, the tortoise has moved slightly further. This process continues infinitely. Every time Achilles reaches where the tortoise was, the tortoise has moved ahead. Therefore, Achilles must complete an infinite number of tasks to catch up. And how can anyone complete an infinite number of tasks in a finite amount of time? Of course, we know from experience that Achilles does overtake the tortoise. Fast things catch up to slow things all the time. But Zeno's paradox reveals something genuinely puzzling about infinity. If space and time are infinitely divisible, if you can keep breaking any distance into smaller and smaller segments without ever reaching a smallest possible piece, then every movement involves crossing an infinite number of points. Every journey, no matter how short, requires an infinite number of steps. How is motion possible at all? Zeno proposed several other paradoxes along similar lines. In one, he argues that an arrow in flight is actually motionless. At any given instant, the arrow occupies a specific position in space. But if it occupies that position, it's not moving. And if time is made up of a series of instants, and at each instant the arrow is stationary, then the arrow never moves. In another paradox, he suggests you can never even start to move, because first you'd have to cover half the distance, but before that, you'd have to cover half of that half, and before that half of that, and so on infinitely. You'd have to complete an infinite number of preliminary steps before you could even begin. These paradoxes bothered people for centuries. They seemed to prove that motion was impossible, which was obviously absurd since motion clearly exists. But if motion exists, something must be wrong with the logic of the paradoxes, and figuring out exactly what was wrong proved remarkably difficult. The paradoxes touch on deep questions about the nature of space and time. Are they infinitely divisible, or is there some smallest possible unit? Is time made of discrete moments, or does it flow continuously? These questions still matter in modern physics. The ancient Greeks' response was largely to throw up their hands. Since infinity created these impossible puzzles, and since we couldn't resolve them satisfactorily, perhaps we should just avoid dealing with infinity altogether. Stick to the finite, to things we can count and measure, to quantities that have definite, manageable values. This avoidance of infinity became deeply embedded in mathematical thinking. For well over 2,000 years, mathematicians were uncomfortable with infinite processes and infinite quantities. They developed clever techniques for working around infinity. When they needed to deal with something that seemed infinite, they'd use limits and approximations instead. They'd get as close as needed without ever actually invoking the infinite itself. This worked remarkably well for practical purposes. You could do geometry, algebra, even early calculus, without ever confronting infinity head-on. But there was always a sense that infinity was lurking in the background. This strange shadow at the edge of mathematical thought. This thing everyone agreed was somehow important, but nobody wanted to examine too closely. It would take until the 19th century, more than 2 millennia after Zeno, before someone finally looked infinity straight in the face and said, "What if we tried to understand it properly? What if, instead of avoiding infinity, we studied it directly, developed a rigorous mathematical theory of it, and figured out what infinity actually is?" The mathematical revolution. Cantor's breakthrough. Georg Cantor was born in 1845 in St. Petersburg, Russia, though he grew up in Germany and spent most of his career there. He was a brilliant mathematician who initially worked on problems in analysis and number theory, fairly conventional topics for his time. But in the 1870s, while investigating questions about trigonometric series and how to represent functions, Cantor stumbled into something that would change mathematics forever. He began thinking about infinite sets, about collections that contain infinitely many objects. And in thinking about them carefully, rigorously, trying to understand them the way a mathematician understands finite sets, he made a discovery that shocked the mathematical world. Cantor proved that there are different sizes of infinity. Not just that infinity is large, but that there are infinitely many different infinities, each larger than the last, forming an endless hierarchy that stretches beyond comprehension. This wasn't philosophy. It wasn't speculation. It was rigorous mathematics, with proofs that could be checked and verified. And it revealed that infinity was far stranger than anyone had imagined. To understand what Cantor discovered, we need to think about what it means for two sets to have the same size. For finite sets, this is straightforward. A set of 3 apples and a set of 3 oranges have the same size because both contain 3 objects. But how do you compare infinite sets? You can't count the elements in an infinite set, so the usual notion of size doesn't work. Cantor realized the solution was to use one-to-one correspondence, a concept that would become fundamental to set theory. Two sets have the same size, or the same cardinality, if you can pair up their elements one-to-one with none left over. Imagine a classroom full of students and chairs. How do you know if there are the same number of students as chairs without counting? Simple. Have everyone sit down. If every chair has exactly 1 student and every student has exactly 1 chair, the sets are the same size. If there are empty chairs, there are more chairs. If students are standing, there are more students. This works regardless of the actual numbers involved. Cantor applied this idea to infinite sets. Consider the set of all natural numbers. 1, 2, 3, 4, and so on forever. This is clearly infinite. Now, consider the set of all even numbers. 2, 4, 6, 8, and so on forever. Is one set larger than the other? Your intuition might say yes. After all, the even numbers are contained within the natural numbers. The natural numbers include both odd and even numbers, so there must be more natural numbers than even numbers, right? But Cantor showed this intuition is wrong when dealing with infinity. You can create a perfect one-to-one pairing between the natural numbers and the even numbers. Pair 1 with 2, pair 2 with 4, pair 3 with 6, and so on. Every natural number n pairs with the even number 2 times n. Every natural number gets exactly 1 even number, and every even number comes from exactly 1 natural number. Nothing is left over in either direction. By the definition of cardinality, these two infinite sets have exactly the same size. This was already strange. An infinite set can have the same size as a proper subset of itself, something that never happens with finite sets. If you remove elements from a finite set, you get a smaller set. But with infinite sets, You can remove infinitely many elements and still have the same size remaining. Cantor called this type of infinity countable infinity, and he used the Hebrew letter aleph with a subscript 0 to represent it. This is aleph null, the smallest infinite size. Cantor proved that many sets we might think are larger than the natural numbers are actually the same size. The set of all integers, positive and negative and 0, is countable. You can list them in a sequence: 0, 1, -1, 2, -2, 3, -3, and so on, pairing each with a natural number. Even more surprisingly, the set of all rational numbers, all fractions, is also countable. This one isn't obvious at all. Between any two fractions, you can always find another fraction. The rationals seem incredibly dense, far more numerous than the integers. And yet Cantor showed you could arrange all the fractions in a list, or a systematic way of counting through them, meaning they were the same size as the natural numbers, same infinity. But then Cantor made his most shocking discovery. He proved that the set of real numbers, all the points on a number line including both rational and irrational numbers, is not countable. It's a larger infinity. The proof is beautiful and has become one of the most famous arguments in mathematics. It's called Cantor's diagonal argument. Suppose, for the sake of contradiction, that the real numbers between 0 and 1 could be listed in a sequence. Write them as infinite decimals, 1 per row. Now, construct a new number as follows. Look at the first decimal place of the first number, and make your new number's first decimal place different from that. Look at the second decimal place of the second number, and make your new number's second place different. Continue this way, making each decimal place of your new number different from the corresponding place in the corresponding number on your list. This new number you've constructed is definitely a real number between 0 and 1, but it can't be anywhere on your list. It differs from the first number in the first place, from the second number in the second place, and so on. It's different from every single number on your supposed complete list. This is a contradiction. We assumed we had a complete list of all real numbers, but we just constructed a real number that isn't on the list. Therefore, no such complete list is possible. The real numbers cannot be put in one-to-one correspondence with the natural numbers. They are uncountable, a strictly larger infinity. Cantor denoted this larger infinity as the cardinality of the continuum, and it corresponds to 2 raised to the power of aleph null. This was revolutionary and deeply disturbing to many mathematicians. It meant that infinity wasn't just one big amorphous concept. There were small infinities and large infinities, and the large infinities were genuinely, mathematically larger. But Cantor didn't stop there. He showed that the process could continue. Take the set of all subsets of the real numbers. This has a cardinality of 2 to the power of the continuum, which is yet larger. Take all subsets of that, and you get an even larger infinity. This process never ends. There's an infinite hierarchy of infinities, each one dramatically larger than the one before. And there's no largest infinity. No matter how large an infinite set you have, you can always construct a larger one by taking its power set. The mathematical universe contains an infinite tower of infinities, each transcending the one below. This vision was beautiful to some and horrifying to others. Cantor faced fierce opposition. Leopold Kronecker, an influential mathematician at the University of Berlin, attacked Cantor's work viciously. He called Cantor a charlatan and a corrupter of youth. He blocked publication of Cantor's papers and prevented him from getting positions at prestigious universities. Kronecker believed that only constructive mathematics was valid, only things you could build up from finite processes. The idea of completed infinities, of infinite sets existing as actual mathematical objects, was anathema to him. The opposition took a toll on Cantor. He suffered from recurring bouts of depression throughout his life. Whether the harsh criticism of his work contributed to his mental health struggles, or whether both stemmed from the same intense, perhaps unstable personality, historians debate. But there's something poignant about the idea that the man who opened up the infinite hierarchy, who showed that infinity was far more vast and strange than anyone had imagined, may have been broken by the infinite complexity he discovered. In his later years, Cantor gained increasing recognition. His work became foundational to modern mathematics. Set theory, which Cantor essentially created, became the underlying framework for all of mathematics. Today, virtually every mathematical concept can be expressed in the language of sets, and the questions Cantor raised about the nature of infinity remain at the cutting edge of mathematical research. He received honors and awards, including the prestigious Sylvester Medal from the Royal Society. But his health continued to deteriorate, and he spent his final years in and out of sanatoriums. He died in 1918 during World War I in a psychiatric clinic, impoverished and worn down by years of struggle. Yet his legacy endures. Cantor showed us that infinity isn't a single monolithic concept, but an intricate landscape with its own structure, its own logic, its own surprises. He demonstrated that we could think about infinity rigorously, prove theorems about it, explore its properties with the same precision we bring to finite mathematics. And in doing so, he revealed that the mathematical universe is far larger and more mysterious than the physical universe could ever be. No matter how large the cosmos might be, no matter how many particles it contains, or how much space it encompasses, mathematics contains infinities that dwarf it, that transcend it, that make the entire physical universe seem like a single grain of sand on an infinite beach. The paradoxes that challenge reality. Once you accept that infinity is a legitimate mathematical concept, once you start treating infinite collections as objects you can reason about, strange things begin to happen. The rules that govern finite quantities stop working. Common sense breaks down. And you find yourself confronting paradoxes that are simultaneously amusing, puzzling, and profoundly revealing about the nature of infinity itself. Perhaps the most famous of these is Hilbert's Hotel, a thought experiment that has become a classic illustration of how infinity behaves in ways that completely violate our intuitions. David Hilbert was one of the greatest mathematicians of the early 20th century. In lectures, he gave in Göttingen, Germany, In the winter of 1924 to 1925, he described an imaginary hotel to help his students understand the properties of countably infinite sets. Picture a hotel with infinitely many rooms, numbered 1, 2, 3, and so on without end. Every single room is currently occupied by a guest. The hotel is completely full. Now, a new guest arrives at the front desk seeking a room. In any normal hotel, the desk clerk would have to apologetically explain that they're fully booked. But this isn't a normal hotel. The clerk smiles and says no problem. Here's what we'll do. We'll ask the guest in room 1 to move to room 2. The guest in room 2 will move to room 3. The guest in room 3 will move to room 4, and so on. Every guest moves up one room number. Now, room 1 is vacant, and the new guest can check in. Everyone has a room. No one has been kicked out. The hotel has absorbed a new guest despite being completely full. This already feels strange, but it gets weirder. Suppose a bus arrives carrying infinitely many new guests, all needing rooms. Can the hotel accommodate them? Absolutely. The clerk asks the guest in room 1 to move to room 2, the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and in general, every guest currently in room N moves to room 2 times N. Now, all the even-numbered rooms are occupied, and all the odd-numbered rooms are empty. There are infinitely many odd-numbered rooms. The infinitely many new guests from the bus can each take an odd-numbered room. Everyone is accommodated. In fact, you can handle infinitely many buses, each carrying infinitely many passengers. Just use a more clever numbering scheme, and there will be room for everyone. The hotel can always accept more guests no matter how full it appears to be. Hilbert's hotel illustrates a fundamental property of infinite sets. For any infinite set, there exist proper subsets that are the same size as the original set. You can remove infinitely many elements and still have the same infinity left. You can add infinitely many elements and still have the same infinity. The concepts of full and empty stop having their usual meanings. A set can be full in the sense that every position is occupied, and yet still have room for more in the sense that you can rearrange things to make space. This might seem like pure abstraction, a mathematical game with no connection to reality, but these ideas have deep implications. In cosmology, some models of the universe suggest infinite space. If space is truly infinite, with infinitely many regions, infinitely many galaxies, infinitely many stars, then Hilbert's hotel logic applies. The universe could expand, creating more space without ever running out of space. New regions could appear between existing regions, just like new hotel guests fitting into a full hotel. The expansion of space in these models isn't about stretching into something. It's about the infinite structure accommodating more of itself. The paradoxes also raise philosophical questions. Consider the concept of motion through an infinite space. If you're traveling through a space with infinitely many regions, have you made any progress when you've crossed a finite number? In one sense, yes, you're further along than when you started. In another sense, no, you're no closer to the end because there is no end. You've covered 0% of an infinite distance no matter how far you go. Concepts like progress and completion become problematic when infinity is involved. Another famous puzzle is called the Ross-Littlewood paradox. Imagine you have an infinite collection of numbered balls and an empty urn. At time 0, you put balls 1 through 10 into the urn and remove ball 1. Half a minute later, you add balls 11 through 20 and remove ball 2. A quarter minute after that, you add balls 21 through 30 and remove ball 3. You continue this process, each step taking half as long as the previous step, so that you complete infinitely many steps in exactly 1 minute. The question: after the minute is up, after you've completed all infinitely many steps, how many balls are in the urn? At each step, you add 10 balls and remove 1, for a net gain of 9 balls. So the number of balls grows. 9, then 18, then 27, and so on. After infinitely many steps, shouldn't there be infinitely many balls in the urn? But here's the twist. Every individual ball gets removed at some point. Ball 1 is removed in the first step. Ball 2 in the second step. Ball n is removed in step n. So after all steps are complete, every ball has been removed, and the urn should be empty. We have 2 perfectly valid lines of reasoning leading to opposite conclusions. Either the urn contains infinitely many balls, or it contains 0 balls. Which is correct? This paradox reveals that infinite processes can be deeply ambiguous. The answer depends on how you approach the infinity, how you structure the limiting process. Different orderings, different ways of taking limits, can lead to different results. Infinity doesn't behave nicely. You can't always trust your intuitions about how infinite processes will turn out. These paradoxes aren't just curiosities. They touch on real issues in physics and philosophy. When physicists encounter infinities in their theories, such as infinities in quantum field theory calculations or singularities in general relativity, they have to ask, does this infinity represent something real, or does it indicate that our theories are breaking down? Often, infinities in physics are signs that we're pushing a theory beyond its valid domain, that we need new physics to replace the old at extreme scales. The mathematical paradoxes of infinity serve as warnings. Infinity is treacherous territory, and we must be extraordinarily careful when we invoke it. Yet, despite the paradoxes, or perhaps because of them, infinity has proven to be an incredibly fruitful concept. By studying these strange behaviors, mathematicians have developed a deep and rigorous theory of infinite sets. Set theory provides a foundation for all of modern mathematics. The paradoxes forced mathematicians to be precise, to develop axioms and formal systems that could handle infinity consistently. And out of that effort came some of the most beautiful and surprising discoveries in the history of human thought. Infinity in numbers, from counting to cardinals. When we think about infinity in the context of numbers, we're usually thinking about never-ending sequences. Start counting. 1, 2, 3, 4. Now keep going. Never stop. You'll never reach the end because there is no end. There's always a next number. This is the infinity of the natural numbers, the most basic and intuitive form of mathematical infinity. But, as Cantor showed us, this is only the beginning. The natural numbers form what's called a countably infinite set. They have cardinality aleph null. This is the smallest infinity, the baseline against which all other infinities are measured. Any set that can be put into one-to-one correspondence with the natural numbers has this same size. And, as we've seen, there are surprising sets that fit this category. The integers, positive and negative, and 0, are countable. You might think adding all the negative numbers would make it bigger, but you'd be wrong. The rational numbers, all possible fractions, are countable. This is perhaps the most counterintuitive example, because the rationals are dense on the number line. Between any two distinct rational numbers, there are infinitely many other rational numbers. And yet, somehow, this dense infinite set is the same size as the much sparser set of integers. The proof involves a clever enumeration scheme that counts through all fractions systematically, making sure none are left out. Once you've shown a set is countable, you've proven it's a relatively small infinity. It's manageable in a certain sense. You can list its elements in a sequence, assign each one a natural number. There's an order to it, a structure you can grasp. But then we encounter the real numbers, and everything changes. The real numbers include not just the rationals, but also the irrationals. Numbers that can't be expressed as fractions. Numbers like the square root of 2, or pi, or e. These numbers have decimal expansions that go on forever without repeating. And, together, the rationals and irrationals form the continuum, the complete number line without any gaps. Cantor proved that this set is uncountable. It has a strictly larger cardinality than the natural numbers. This is often denoted as C, the cardinality of the continuum, or as 2 to the power of aleph null. How much bigger is the continuum than the natural numbers? This is a surprisingly difficult question. Cantor spent much of his career trying to answer it. He formulated what's called the continuum hypothesis, the claim that there is no set whose cardinality is strictly between that of the integers and that of the real numbers. In other words, the continuum is the very next infinity up from countable infinity. There's no intermediate size. This hypothesis seemed plausible to Cantor, but he couldn't prove it. He tried for years and failed. In 1900, David Hilbert included the continuum hypothesis as the first problem in his famous list of 23 unsolved mathematical problems, highlighting its importance. Mathematicians worked on it throughout the 20th century. Then came two shocking results. In 1940, Kurt Gödel proved that the continuum hypothesis is consistent with the standard axioms of set theory. You can assume it's true, and you won't run into any contradictions. But in 1963, Paul Cohen proved that the negation of the continuum hypothesis is also consistent with those axioms. You can assume it's false, and you still won't get contradictions. Together, these results mean that the continuum hypothesis is independent of the standard axioms. It can't be proved or disproved using the usual rules of mathematics. This was a profound and disturbing discovery. It means that the question of whether there's an infinity between countable and continuum is, in a precise mathematical sense, undecidable. You can choose to work in a mathematical universe where the continuum hypothesis is true, or one where it's false, and both choices are equally valid. The structure of infinity beyond the countable depends on assumptions that go beyond the basic axioms of set theory. This opened up a whole new area of mathematical research. Set. Theorists began exploring different possible axioms you could add to extend set theory, each choice leading to a different landscape of infinities. Mathematics became, in a sense, pluralistic. There isn't just one mathematical universe. There are many possible universes, each with its own properties, its own structure of infinite sets. And we get to explore them all, see what happens in each, compare and contrast. It's like theoretical physics, where we consider different possible physical laws and see what kinds of universes they produce. But in mathematics, we can actually construct these universes rigorously and explore them completely. Beyond the continuum, the infinities keep growing. Cantor showed that for any set, the set of all its subsets is strictly larger. So, if you take all possible collections of real numbers, all possible sets of real numbers, you get an infinity larger than the continuum, and you can repeat this process indefinitely. Each time, you get a bigger infinity. There's no upper limit. The hierarchy extends forever. Mathematicians have developed a rich vocabulary and theory for dealing with these transfinite numbers. There are cardinal numbers which measure size and ordinal numbers which measure order. The arithmetic of transfinite numbers is strange and wonderful. You can add them, multiply them, even exponentiate them, and the results don't always behave the way finite arithmetic does. For example, 1 plus omega equals omega, but omega plus 1 is different from omega. The order matters in infinite arithmetic in ways it doesn't for finite numbers. This mathematical structure is one of the great achievements of human thought. We started with the simple question of what it means for two collections to have the same size, and we ended up discovering an infinite hierarchy of infinities, each with its own properties, its own mysteries. And this hierarchy isn't just abstract nonsense. It shows up in profound ways throughout mathematics. Questions about the size of infinite sets appear in topology, in analysis, in logic, in nearly every branch of advanced mathematics. Understanding infinity, truly understanding it at this deep level, is essential to understanding the mathematical universe as a whole. And yet, for all this understanding, infinity remains mysterious. The independence of the continuum hypothesis reminds us that there are limits to what we can know, questions we can't settle, choices we have to make that aren't dictated by logic alone. Infinity pushes us to the edge of what mathematics can say definitively. Infinity between the numbers. There's a particular kind of infinity that's both intuitive and profoundly strange when you think about it carefully. The infinity lurking between two numbers on the number line. Consider the distance between 0 and 1. It seems like a definite, finite quantity. You can measure it. You can hold up your hands 1 unit apart and say, "This is the distance from 0 to 1. And yet, hidden within that finite span is an infinity so dense, so rich, that it contains more points than you can count, even with all of eternity. Let's start with something simple. Between a 0 and 1, there are infinitely many rational numbers, infinitely many fractions. You have 1/2, 1/3, 1/4, and so on forever. You have 2/5, 3/7. Any fraction you can imagine where the numerators and denominator are whole numbers and the result falls between 0 and 1. These fractions are everywhere. Between any two fractions, you can always find another fraction. Just take their average. If you have 1/3 and 1/2, the average is 5/12, which falls right between them. And between 1/3 and 5/12, you can find another fraction, and so on forever. The rationales are dense. No matter how close together you pick two fractions, there are infinitely many more fractions between them. And yet, as we've learned from Cantor, the rational numbers between 0 and 1 are countably infinite. You could, in principle, list them all in a sequence. It would be a very long list, infinitely long, but it's the same size infinity as the counting numbers. But the rationals, despite being dense and despite being infinite, don't actually fill up the interval. There are gaps, places where the rationales aren't. These gaps are filled by the irrational numbers. Consider the square root of 2 divided by 2, which is approximately 0.707. This number is between 0 and 1, but it's not a fraction. It can't be written as a ratio of whole numbers. Its decimal expansion goes on forever without repeating. 0.7, 0.71, 0.6781, and continues infinitely without any pattern. This is an irrational number, and there are infinitely many of them between 0 and 1. In fact, there are uncountably many of them, a strictly larger infinity than the rationales. This leads to a remarkable fact. Almost all real numbers between 0 and 1 are irrational. The rationales, despite being infinite and despite being dense, form a vanishingly small subset of the real numbers. If you were to pick a random real number between 0 and 1, the probability that it would be rational is 0, not because it's impossible, but because the rationales are negligible compared to the vastness of the irrationals. This is hard to wrap your mind around. We tend to think about numbers in terms of fractions and decimals, which are all rational or at least expressible in rational terms. But the typical real number is far stranger than anything we can write down explicitly. Most real numbers are irrational, and moreover, most of them are transcendental, meaning they're not the solution to any polynomial equation with integer coefficients. Numbers like pi and e are transcendental, but they're actually quite special. Most transcendental numbers are far more random, far less structured than these famous constants. So, between 0 and 1, we have an uncountable infinity of real numbers. But we can go further. Consider all possible sets of real numbers between 0 and 1. How many such sets are there? This is the power set of the continuum, and it's a strictly larger infinity. And we can take the power set of that, and so on, building an infinite tower of ever larger infinities, all contained conceptually within that innocent-looking interval from 0 to 1. In a sense, infinity is most at home in the gaps between things. When we divide a line segment in half, then divide those halves in half, and continue forever, we're performing an infinite process within a finite space. Zeno's paradoxes exploit this. To travel 1 meter, you must first travel half a meter, then half of what remains, then half again, summing an infinite series of distances. That we can do this, that we can traverse infinitely many intervals in a finite time, suggests that infinity and finitude are intertwined in subtle ways. Modern mathematics resolves Zeno's paradoxes using the concept of limits and infinite series. The sum of 1/2 plus 1/4 plus 1/8, and so on, equals exactly 1. The infinite sum converges to a finite value. This is how we make sense of infinite divisibility. The infinite doesn't overwhelm the finite. It's structured in such a way that it adds up to something manageable. But this resolution comes with its own mysteries. How can infinitely many things sum to something finite? The answer lies in the structure of the sum, in the fact that the terms get smaller and smaller in just the right way. But conceptually, it's still strange. We're adding up infinitely many positive quantities and getting a finite answer. This works mathematically, but it challenges our intuitive notion of addition. And it reveals that infinity is always lurking just beneath the surface of everyday mathematics. Every time you use a decimal expansion, every time you think about continuity or smoothness, you are implicitly invoking infinite processes. Calculus, the mathematics of change, is built entirely on limits and infinite processes. When we take a derivative, we're examining the behavior of a function at infinitesimally small scales, looking at what happens as intervals shrink toward zero. When we integrate, we're summing up infinitely many infinitesimal pieces. The entire edifice of modern science rests on this mathematical foundation that treats infinity as a tool, as something we can manipulate and control. But does this mathematical infinity correspond to anything in physical reality? That's a deeper question, one that we'll explore more later. For now, what's clear is that mathematically, infinity between the numbers is not just possible, but essential. Without it, we wouldn't have continuous mathematics, wouldn't have calculus, wouldn't have most of modern science. The infinite is woven into the very fabric of our mathematical description of the world. Infinity in space and time. When we look up at the night sky, one of the most natural questions we can ask is, does it go on forever? Is space infinite, or does it have an edge somewhere? And if it does have an edge, what's on the other side of that edge? These questions feel simultaneously childlike and profound. They're the kind of questions a 5-year-old might ask, and they're also the kind of questions that cosmologists spend their careers trying to answer. For most of human history, we had no good way to even approach these questions scientifically. The universe seemed vast beyond comprehension, but whether it was infinite was more a matter of philosophy than science. Aristotle believed the cosmos was finite, bounded by the sphere of fixed stars. Medieval thinkers debated whether an infinite universe would impinge on God's infinity. The question was tangled up with theology and metaphysics in ways that made it hard to address empirically. Then, in the 20th century, everything changed. Einstein's general theory of relativity published in 1915, provided a mathematical framework for describing the universe as a whole. Suddenly, cosmology became a science. We could write down equations describing the evolution of space and time themselves, and we could test these equations against observations. One of the first things Einstein noticed was that his equations didn't allow for a static, eternal universe. The universe had to be either expanding or contracting. He initially found this result so troubling that he modified his equations by adding a cosmological constant to force a static solution. But then, in the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us, and the more distant they are, the faster they're receding. The universe is expanding. Einstein later called his cosmological constant his greatest blunder. An expanding universe raises immediate questions about infinity. If the universe is expanding, what is it expanding into? The answer general relativity gives is surprising. It's not expanding into anything. Space itself is expanding. The distance between galaxies is increasing, not because they're moving through space, but because the space between them is growing. This is mind-bending. We're used to thinking of space as a fixed stage on which events play out. But in relativity, space is dynamic, something that can stretch and warp. Now, if space is infinite, then it's been infinite the entire time it's been expanding. An infinite universe doesn't become infinite by expanding. It starts infinite and stays infinite, just with the distances between things increasing. This is where Hilbert's hotel logic applies. An infinite space can expand everywhere without running out of room, just like the hotel can always accommodate more guests. But is space actually infinite? This is still an open question in cosmology. What we can observe is only a finite portion of the universe, bounded by the distance light has been able to travel since the Big Bang. This is called the observable universe, and it has a radius of about 46 billion light-years. Beyond that, light hasn't had time to reach us, so we can't see what's there. The observable universe is definitely finite, containing perhaps 2 trillion galaxies. But the entire universe could be much larger, possibly infinite. Current observations suggest that space is very close to being flat, meaning it has no overall curvature. In general relativity, a flat universe extending infinitely is a perfectly consistent solution. If space is flat and extends forever, then there are infinitely many galaxies out there beyond what we can see, infinitely many stars, infinitely many planets. Everything that can happen does happen somewhere, infinitely many times. This leads to some wild implications. In an infinite universe, with infinitely many configurations of matter, every possible arrangement occurs infinitely often. There would be infinitely many planets exactly like Earth, with people exactly like you living lives exactly like yours, and infinitely many that are slightly different, exploring every possible variation. This idea, sometimes called the infinite universe hypothesis, is philosophically dizzying. It suggests that everything that can exist does exist, somewhere out there in the infinite cosmos. Of course, we have no way to verify this. Those other versions of you are forever beyond our ability to observe or communicate with. They're outside our cosmic horizon. But if the universe is truly infinite, they're out there, as real as you are. Some cosmologists find this beautiful. Others find it troubling. An infinite universe seems to eliminate uniqueness, to make every event, no matter how special it seems, just one of infinitely many occurrences. Then there's the question of time. We know the universe has a finite age, about 13.8 billion years since the Big Bang. But does time extend infinitely into the future? Will the universe exist forever, or will it eventually end? Current observations suggest the expansion of the universe is accelerating, driven by mysterious dark energy. If this continues, the universe will expand forever, becoming increasingly cold and empty as stars burn out and galaxies drift apart. Eventually, in the inconceivably distant future, the universe would reach a state of maximum entropy, a heat death where no meaningful change can occur. But this state could persist eternally. Time would continue infinitely, but nothing interesting would happen in it. Alternatively, some speculative theories propose that the universe could collapse back on itself in a big crunch, or that our universe is just one bubble in an eternally inflating multiverse where new universes are constantly being created. In these scenarios, time might not have a simple beginning and end, but a more complex, possibly infinite structure. The question of whether actual infinity exists in space and time remains open. Mathematically, we can describe infinite universes with no problem. The equations handle it fine. But does nature actually implement infinity, or does it always keep things finite, just enormously large? Some physicists argue that infinity is a red flag indicating that our theories are incomplete. When infinities appear in calculations, such as the singularities in black holes or the infinite energy densities at the Big Bang, we usually interpret them as signs that we need better physics. Quantum gravity, when we finally figure it out, might eliminate these infinities and replace them with large but finite quantities. Others argue that infinity is probably real, that there's no reason to think the universe is finite if our best theories allow for it to be infinite. This debate touches on deep issues about the relationship between mathematics and physics, about whether the universe is obligated to be mathematically convenient, about what kinds of concepts can correspond to physical reality. And it's a debate we likely won't resolve anytime soon. The physics of infinity. Physics has a complicated relationship with infinity. On one hand, the mathematical tools physicists use are saturated with infinite concepts. Calculus, which is foundational to all of physics, is built on infinite processes and infinitesimal quantities. Quantum mechanics describes particles with wave functions that extend infinitely through space. General relativity allows for infinite spacetimes. The very concept of a field, fundamental to modern physics, involves assigning values to infinitely many points in space. And yet, whenever actual infinities show up in the results of physical calculations, physicists get nervous. Infinities in physics are usually problems to be solved rather than answers to be accepted. Let's start with the most dramatic infinities in physics, singularities in general relativity. Einstein's theory predicts that under certain conditions, gravity can become so strong that it crushes matter to infinite density in a region of zero volume. These are singularities, and they appear in two main contexts: at the centers of black holes and at the Big Bang origin of the universe. When a massive star runs out of fuel and collapses, if it's heavy enough, nothing can stop the collapse. The star's core implodes, and general relativity predicts that it forms a singularity, a point where density, gravity, and space-time curvature all become infinite. This singularity is hidden behind an event horizon, a boundary that nothing, not even light, can cross from inside to outside. What we observe from the outside is a black hole, a region of space-time from which no information can escape. Inside that event horizon, at the very center, sits the singularity. But what does it mean for density to be infinite? Can this really happen in nature? Most physicists think the answer is no. They believe that when we calculate infinite density, we're pushing general relativity beyond its domain of validity. General relativity is a classical theory, meaning it doesn't incorporate quantum mechanics. At extremely small scales and extremely high densities, quantum effects become important. We need a theory of quantum gravity to describe what really happens inside a black hole. And most physicists expect that such a theory will eliminate the singularity, replacing it with something extreme but finite. The same issue arises with the Big Bang singularity. If we follow the expansion of the universe backward in time, general relativity predicts that everything was squeezed into an infinitely dense, infinitely hot state at time zero. This is the Big Bang singularity. But again, most physicists don't think the universe actually had infinite density. Instead, they believe that as we approach the earliest moments, quantum effects become crucial, and we need quantum gravity to describe what happened. Perhaps the universe bounced from a previous contracting phase. Perhaps time itself becomes fuzzy at the quantum level, and the concept of a first moment doesn't quite make sense. Various proposals exist, but they all aim to eliminate or reinterpret the singularity, to avoid actual infinity in the description of reality. Infinities also plague quantum field theory, the framework for describing particle physics. When physicists calculate the properties of particles or the probabilities of various interactions, they often encounter integrals that diverge, that give infinite results. These infinities don't represent real physical predictions of infinite energy or infinite probability. Rather, they're artifacts of the calculation methods, indications that something is being treated incorrectly. Physicists have developed techniques called renormalization to handle these infinities. Essentially, renormalization involves carefully subtracting infinities in such a way that what remains is finite and matches experimental observations. This might sound like cheating, but it's actually deeply principled. The infinities arise because we're treating particles as point-like objects, which is an idealization. In reality, at extremely short distances, new physics that we haven't included becomes important. Renormalization is a way of absorbing our ignorance about short-distance physics into a few measurable parameters. Once you have done that, the theory makes finite, testable predictions that turn out to be extraordinarily accurate. Quantum electrodynamics, the theory of electrons and light, is the most precisely tested theory in all of science, with predictions matching experiments to better than 1 part in a trillion. And yet, it's a theory that required taming infinities to make sense. Still, not all infinities in quantum field theory can be renormalized. Some theories are non-renormalizable, meaning the infinities can't be consistently removed, and the theory loses predictive power at high energies. This is generally interpreted as a sign that the theory is only an effective description, valid at low energies and needs to be replaced by something more fundamental at higher energies. For instance, general relativity itself is non-renormalizable when you try to quantize it. This is one of the main reasons physicists believe we need a new theory, a quantum theory of gravity, to fully describe the universe. All of this suggests a pattern. Infinities in physics are usually not regarded as real features of nature. They're signs that our theories are incomplete or are being pushed beyond their limits. When we develop better theories, the infinities typically disappear, replaced by large but finite quantities or by more sophisticated structures that don't blow up. And yet, there's a tension here. The mathematical tools we use embrace infinity. We treat space as a continuum with infinitely many points. We treat time as flowing continuously through infinitely many instants. We describe fields that assign values to every point in space, an infinite amount of information. If nature really is discrete at the smallest scales, if there is a fundamental graininess to space and time, then these infinite continuum models are just approximations. Incredibly good approximations, but not the full truth. On the other hand, if the continuum is real, if space and time are genuinely smooth all the way down, then infinity is woven into the fabric of reality itself. We don't yet know which of these pictures is correct. The physics of infinity remains one of the deepest open questions in fundamental science. Infinity in everyday life. For all its abstraction, infinity isn't just something that shows up in advanced mathematics and theoretical physics. There are echoes of infinity all around us, in patterns and processes we encounter in daily life, if only we know how to look for them. One of the most beautiful examples is the fractal. Fractals are geometric shapes that exhibit self-similarity at different scales. If you zoom in on a portion of a fractal, you see structure that looks like the whole, and if you zoom in further, the pattern repeats again. This self-similarity can continue infinitely. The most famous fractal is probably the Mandelbrot set, a mathematical object of stunning complexity and beauty. The Mandelbrot set is generated by a simple iterative equation, but when you plot which numbers remain bounded under iteration, you get an infinitely intricate shape. The boundary of the Mandelbrot set is endlessly detailed. No matter how much you zoom in, you keep finding new structures, new patterns, new miniature copies of the whole set. You could explore it forever and never see everything. But fractals aren't just mathematical curiosities. They appear throughout nature. Coastlines are fractal-like. Their length depends on the scale at which you measure them. If you use a kilometer-long ruler, you get one length. If you use a meter-long ruler, following more of the ins and outs, you get a longer length. As your ruler gets shorter, the measured length increases, potentially without bound. Mountains, clouds, lightning bolts, river networks, blood vessels, trees, all of these exhibit fractal-like properties. They have structure at many different scales, and that structure often repeats in similar ways. Nature seems to love fractals, perhaps because they're efficient. A fractal branching pattern, like the bronchi in your lungs or the branches of a tree, can cover a large area or volume, while minimizing the total length of the branches. The infinite complexity of fractals is nature's way of solving optimization problems. Then there's recursion, a concept from computer science and mathematics where something is defined in terms of itself. A recursive process is one that calls itself, creating a potentially infinite loop unless there's a stopping condition. Many algorithms in computing are recursive because recursion can elegantly express complex operations. But recursion also shows up in art and literature. A story within a story within a story, like the Arabian Nights where Scheherazade tells tales that contain other tales, is recursive. The Droste effect, where an image contains a smaller copy of itself, which contains an even smaller copy, and so on, is recursive. If you've ever stood between two mirrors and seen your reflection reflected infinitely in both directions, you've experienced recursion. These are finite approximations to an infinite process. The mirrors don't actually reflect infinitely. Eventually, light fades or angles shift. But they gesture toward infinity, giving us a glimpse of what infinite recursion would look like. Even something as simple as counting is an infinite process. When we teach children to count, we teach them that there's always a next number. No matter what number you say, you can always add one and get a bigger number. This is one of the first abstract ideas we encounter, and it's fundamentally about infinity. The fact that children can grasp this, can understand that counting never ends, even though they've only counted to 100 or 1,000, shows that the human mind has some intuitive grasp of the infinite, even if we can't visualize it or fully comprehend it. We use infinite processes in practical ways all the time. When we calculate the decimal expansion of pi, we're performing an infinite computation, though we stop after however many digits we need. When we use iterative methods to solve equations numerically, we're approximating an infinite process with a finite one. Engineers, scientists, and mathematicians rely on these approximations constantly. The infinite is too large to handle directly, but we can get as close as we need by going far enough into the process. Infinity also appears in philosophy and everyday reasoning in more subtle ways. When we think about possibilities, we're often thinking about infinite sets. The future is infinite in the sense that there are infinitely many possible futures, infinitely many ways things could unfold. When we make decisions, we're navigating this infinite landscape of possibility, trying to choose a path that leads somewhere good. Of course, we can't actually consider infinitely many options. We simplify. We use heuristics. We make do with finite minds in an infinite conceptual space. But the infinity is there, lurking in the background, shaping the structure of the problem. The concept of potential, of what could be, is inherently infinite. As long as change is possible, as long as things can be different from how they are, infinity is present as the open-ended nature of existence. The mind-bending implications. When you really sit with infinity, when you let it into your mind, and try to grasp what it means, it starts to affect how you see everything. Infinity isn't just a mathematical concept or a cosmological question. It's a lens that transforms how we think about existence, meaning, possibility, and ourselves. One of the most profound implications of infinity is what it suggests about uniqueness and value. In a finite universe, events can be unique. This particular configuration of atoms, this specific moment in time, this individual, consciousness, might be the only one of its kind. There's something special about it. But in an infinite universe, uniqueness becomes problematic. If there are infinitely many planets, infinitely many civilizations, infinitely many versions of history playing out across infinite space, then nothing is truly unique. Every event, no matter how special it seems, is happening infinitely many times elsewhere. Does this make things meaningless? Some philosophers argue yes, that in an infinite universe, nothing really matters because it's all just one instance among infinite instances. But others argue the opposite, that meaning doesn't come from global uniqueness, but from local context. The fact that there might be another you somewhere else in the cosmos doesn't diminish the importance of your experiences here and now. Your joys and sorrows are real to you, and that's what matters. Infinity doesn't erase meaning, it just reframes it. Another implication concerns determinism and free will. If we live in an infinite universe or an infinite multiverse where every possibility is realized somewhere, then, in some sense, everything that can happen does happen. Somewhere out there or in some parallel reality, every choice you could make is being made. Does this mean your choices here don't matter? Or does it mean that your choices determine which branch of infinity you personally experience? These are deep questions without clear answers, but infinity forces us to confront them. Infinity also challenges our concepts of probability and likelihood. In a finite universe, we can talk about the probability of an event as the fraction of possible outcomes in which it occurs. But in an infinite universe, this becomes strange. If infinitely many things happen, and both event A and event B happen infinitely often, what does it mean to say one is more probable than the other? Mathematicians have developed sophisticated theories of measure to handle these questions, but they don't fully resolve the conceptual difficulties. Infinity makes probability slippery. Then there's the question of consciousness and identity. What does it mean to be you in an infinite universe? If there are infinitely many people physically identical to you, down to the last atom, experiencing the exact same thoughts and memories at this exact moment, are they all you? Or are you just one of them? Is personal identity tied to a specific physical location in space-time, or is it something more abstract? If you could be duplicated perfectly, would both copies be you, or would they be two separate individuals who happen to be identical? Infinity makes these questions more than thought experiments. In an infinite universe, they might be actual facts about reality. Infinity also touches on questions about God and spirituality, though in ways that depend heavily on one's theological framework. Some religious traditions embrace infinity as an attribute of the divine. God is infinite in power, knowledge, presence. The infinite nature of the universe, if it is infinite, might be seen as a reflection of divine infinity. But infinity also creates puzzles. If there's an infinite past, do we need a first cause? If the universe can be infinite, does that compete with or complement the concept of an infinite God? Different traditions answer differently, but infinity is central to many of these discussions. Perhaps most fundamentally, infinity reveals the limits of human understanding. We can think about infinity, reason about it, prove theorems about it, but we can't really comprehend it in the way we comprehend finite things. Infinity is always beyond our grasp, always exceeding our ability to visualize or intuit. And yet, we can understand its formal properties. We can know that some infinities are larger than others, even if we can't picture what that really means. This suggests something profound about the nature of knowledge and understanding. There are things we can know without fully comprehending, truths we can access through logic and mathematics even when they transcend our direct experience. Infinity is humbling. It reminds us that the universe, whether physical or mathematical, is far larger and stranger than we can ever fully grasp. Our minds are finite, bound by finite brains with finite neurons processing finite amounts of information. And yet, we can conceive of the infinite, can reason about it, can even, in some sense, explore it. This is one of the most remarkable features of human consciousness, our ability to think beyond ourselves, to reach toward concepts that exceed us. Infinity is the ultimate example of this reaching, this yearning to understand what lies beyond all boundaries. Modern perspectives and continuing mysteries. Today, more than a century after Cantor, infinity remains at the frontier of mathematical and scientific research. We've learned an enormous amount, but many fundamental questions remain unanswered, and new mysteries have emerged as our understanding has deepened. In mathematics, set theorists continue to explore the landscape of infinite cardinals. They've discovered that the universe of sets is far richer and more complex than Cantor ever imagined. Different axioms beyond the standard Zermelo-Frenkel set theory lead to different structures of infinity. There are large cardinal axioms, assumptions about the existence of infinities so large that they transcend anything we can construct from smaller infinities. These large cardinals have remarkable properties and connections to other areas of mathematics. Whether they actually exist in some Platonic sense, or whether we're just exploring different consistent logical systems, is a matter of philosophical debate. Computability theory, the study of what can be computed, also encounters infinity in interesting ways. A Turing machine, the theoretical model of computation, can run for infinitely many steps, though in practice all real computers are finite. But there are problems that require infinite computation to solve, questions that can't be answered by any finite algorithm. Gödel's incompleteness theorems show that in any sufficiently powerful mathematical system, there are true statements that can't be proved within that system. This is closely related to infinity. The set of all true mathematical statements is infinite, and no finite set of axioms can capture all of them. There will always be truths beyond what any particular axiom system can reach. This suggests that mathematical truth itself has an infinite character, that the space of mathematical facts extends infinitely beyond any finite description. In physics, the question of whether infinity is real remains open and contentious. Some physicists hope that a final theory of quantum gravity will eliminate all infinities, that the universe at its deepest level will turn out to be finite, or at least not contain actual infinities. Others think that's wishful thinking, that infinity is probably an ineliminable feature of reality. We won't know until we have better theories and better experiments. One area where infinity plays a central role is in thermodynamics and statistical mechanics. These fields deal with systems containing huge numbers of particles, and many results are phrased in terms of the thermodynamic limit, where the number of particles goes to infinity. Real systems are finite, but the infinite limit often provides an excellent approximation and reveals underlying principles that would be obscured in a finite system. This is an example of infinity serving as a useful idealization, a simplifying assumption that makes the mathematics tractable. Another modern context where infinity appears is in the study of complexity and chaos. Chaotic systems are extremely sensitive to initial conditions, meaning tiny changes at the start can lead to vastly different outcomes later. In principle, predicting the long-term behavior of a chaotic system requires infinite precision in knowing the initial state. Since we can never have infinite precision, chaotic systems are inherently unpredictable beyond a certain time horizon. Infinity enters here as a limit. The limit of what we can know, the limit of what we can predict. And then there's the practical question of computation and resources. Our computers are finite. Our lifetimes are finite. Our universe might be finite. How do we work with infinity given these constraints? We approximate. We truncate infinite series. We discretize continuous spaces. We use finite models to represent infinite processes. All of applied mathematics is, in a sense, the art of replacing infinity with something finite that's good enough for our purposes. But we always have to be aware that we're making approximations, that the infinite reality we're modeling isn't fully captured. The philosophical questions about infinity haven't been resolved either. Is mathematical infinity a real thing, existing in some Platonic realm of perfect forms? Or is it a creation of the human mind, a useful fiction that helps us organize our thoughts but doesn't correspond to anything outside ourselves? Does the physical universe actually contain infinite quantities, or does it just appear to because we haven't looked closely enough? These questions might not have definitive answers, or the answers might depend on what we mean by real and exist. What we can say is that infinity, whether real or not, is an indispensable tool for understanding the universe and our place in it. Infinity has also inspired art and literature, philosophy and theology, in ways that go far beyond mathematics and science. The idea of the infinite has shaped human culture profoundly. From the sublime in romantic poetry to the cosmic horror of Lovecraft to the mind-bending science fiction of authors exploring infinite universes and eternal recurrence, infinity has been a source of inspiration and terror, beauty and dread. It represents the ultimate unknown, the space beyond all maps, the question without answer. Closing reflection. And so, We come to the end of our journey through infinity, though of course there is no end to infinity itself. We've traveled from the ancient Greeks wrestling with paradoxes, to Cantor opening up infinite hierarchies of ever larger infinities, to Hilbert's strange hotel where a full house always has room for more. We've peered into the questions of whether the cosmos is infinite, whether infinity exists in the fabric of reality, whether our finite minds can truly grasp something with no boundaries at all. And what have we learned? That infinity is strange, beautiful, terrifying, and profound. That it sits at the edge of everything we can understand, beckoning us forward while reminding us of our limits. That mathematics can handle infinity with precision and rigor, even as it reveals paradoxes and undecidable questions. That physics encounters infinity again and again, sometimes as a problem to be solved, sometimes as a hint of deeper truths. Infinity challenges us to think beyond ourselves, beyond our immediate experience, beyond everything we can see or touch or count. It asks us to embrace concepts that transcend comprehension while still reasoning about them carefully. It teaches us humility, showing us that the universe, whether mathematical or physical, is far vaster than we can ever fully grasp. And yet, infinity also demonstrates the power of human thought. We can conceive of the infinite. We can reason about it, prove theorems about it, build theories that incorporate it. Our finite minds can reach toward the infinite, can touch it, even if we can't hold it. This is one of the deepest mysteries about consciousness itself. How can finite beings think about infinity? How can a physical brain, made of a finite number of atoms operating according to finite physical laws, generate thoughts about the boundless? Perhaps the answer is that infinity isn't really a thing we understand directly. We understand it through its properties, through the logical relationships it enters into, through the role it plays in our theories. We don't comprehend infinity the way we comprehend 3 apples or 5 feet. We comprehend it formally, abstractly, through the lens of mathematics and logic. And that's enough. That's how understanding works when we push beyond direct experience. If you've found this exploration meaningful, if these ideas have sparked something in you, I would truly appreciate it if you'd consider liking this video and subscribing to the channel. Your support helps these thoughtful journeys reach others who are curious about the deep questions that make us human. It helps us build a community of people who aren't afraid to wonder, to question, to sit with concepts that break our brains just a little bit. For now, as you settle into rest, let these ideas drift through your mind without trying to hold them too tightly. Let yourself feel the enormousness of infinity, the strangeness of it, the beauty of it. Think about how between any 2 numbers there are infinitely many more numbers, how the universe might extend forever in every direction, containing infinite worlds, infinite possibilities. How some infinities are larger than others, a fact so counterintuitive it seems impossible. And yet it's true, provably true. Think about how you, with your finite mind, can conceive of all this, can think about infinity even though you'll never fully grasp it. That's its own kind of miracle. The concept of infinity reminds us that there are always mysteries beyond what we know, always more to discover, always deeper questions to ask. It keeps us humble and keeps us curious. It challenges us to expand our minds and accept that some things will always exceed our understanding. And maybe that's okay. Maybe that's even beautiful. The universe doesn't owe us comprehensibility. The fact that we can understand as much as we do is remarkable enough. So let your thoughts drift now. Let the infinite spaces between the numbers call to you softly. Let the endless expanse of possible futures and possible worlds wash over you like gentle waves. Let the paradoxes and the mysteries sit with you, not as problems to be solved before you sleep, but as companions, as reminders of how vast and strange and wonderful reality is. You are finite, yes, but you are part of something infinite. You are a small piece of a cosmos that might go on forever, a brief moment in a time that has no end. And in that small, finite space you occupy, you have the astonishing ability to think about the infinite, to wonder about it, to be amazed by it. That wonder is precious. Hold on to it, even as you let everything else go. The infinite will still be there tomorrow, waiting to challenge you, to inspire you, to remind you that there is always more. Always more to learn, more to discover, more to wonder about. There is no end to the questions we can ask, no limit to the mysteries we can explore. That's what infinity means. Not just that things go on forever, but that there's always another level, always a deeper truth, always a new perspective that makes everything look different. And that, more than anything, is the gift infinity gives us. It tells us that the adventure of understanding never ends. Rest well. Let these ideas settle into your dreams. And know that when you wake, the infinite will still be there, patient and eternal, ready for you to explore it once again. Good night.